So we're going to be adding and subtracting or finding sums and differences of both radicals and exponents. So these first several examples will be adding and subtracting radicals, and then we'll look at adding and subtracting things with exponents. So they're going to be similar, only like radicals, like radical expressions may be added or subtracted. And like radical expressions means they have to have the same index. Like they all have to be square roots or they have to be cube roots. I should say only square roots can be added to square roots and cube roots to cube roots, and they have to have the same number under the radical. If they don't have both of those things, they can't be added. So as we come across to this first example, we need to look and see if we have like radicals. Well, these are all square roots, and they're all square roots of 2, so they can be added. So what we'll do here is we'll look at this first one, this last one, and realize this is a 1 square root of 2. And once you have like radicals, it's very much the same as adding like terms. And so you really just add the coefficients. So we have 5 square root of 2 plus 6 plus 1. So 5 plus 6 plus 1 is 12. So we have 12 times the square root of 2. And again, that's similar to adding if these were variables. If we had a 5x plus a 6x plus an x or a 1x, that's just 12x. So it's the same idea. You don't do anything with the radical. You still leave it a square root of 2. You don't add what's inside here when you're adding the radical, so 12 root 2. The next example here has no like radicals to start with, but we did learn how to simplify radicals. And what we're going to do is we're going to think of each of these radicals and see if we can simplify them. So we have a 2 still out here, and can we simplify the square root of 8? Well, we want to think if there are any perfect squares that go into 8, and 4 does. So this we can rewrite as the square root of 4 times the square root of 2. The 12 we can think of, well, 12 has a 4 that goes into it, so that's a perfect square, so that's the square root of 4 times the square root of 3. And then 32, you have to be careful, 4 does work, but a better perfect square is 16, or the largest perfect square that goes into that is 16, so that's the square root of 16 times the square root of 2. And so we're going to simplify our perfect squares. So this is we still have our 2, the square root of 4 is 2, and root 2, plus square root of 4 is 2, and we have the root 3, and then square root of 16 is 4 root 2. Well, over here we have a 2 times 2. This is the same as a 4. So we have a 4 root 2 and a minus 4 root 2. Well, those are like radicals, both square roots of 2, so you have 4 of them minus another 4 of them is 0. So really we're just left with 2 times the square root of 3, or 2 root 3, we might say. All right, the last one here has a cubed root of 54, square root of 20, minus 5 root 2 plus root 45. So we'd have to have the same index and the same number under the radical, so this is a cubed root, so this probably won't be able to be combined with any of these other ones. But we still do want to simplify it if possible. Now, we want to think, is there a perfect cube that goes into 54? So our perfect cubes are 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So 27 goes into that. So what we can do is we can split this up into the cubed root of 27 times, and 27 times what equals 54? Well, 2 times the cubed root, that didn't turn out very well, of 2. And then 20, that's any perfect squares into 20. Well, 4 goes into that, so square root of 4 times the square root of 5. We can't simplify the square root of 2, so it's just minus 5 root 2. And then 9 goes into this is square root, perfect square that goes into this is 9, so we can think of this as the square root of 9 times the square root of 5, because 9 times 5 is 45. And now we can simplify. Cubed root of 27 is 3, so we have a 3 times the cubed root of 2 plus square root of 4 is 2, so 2 times the square root of 5 minus 5 root 2, and then plus 3 root 5. Now we're looking for like terms or like radicals. You might look at the first one and then this third one, and they both have a 2 underneath, but they are not like radicals because they don't have the same index. So we can't combine those. We do, however, have a square root of 5 and then another square root of 5. So we can simplify that. So we'll keep this the same. So 3 cubed root of 2. We'll add these two. A 2 root 5 plus a 3 root 5 is 5 root 5. And then minus 5 root 2. And that would be the simplified, or the simplified version of that. So that's adding radicals. To add radicals, you need the same index in your radical and the same number under the radical. And obviously, as we saw in these second two examples, that you need to simplify your radicals first, and then sometimes you can add ones that are like. And once again, do not change the radical when you add. So we added a 2 root 5 and a 3 root 5, so our answer was 5, and you still keep the square root of 5. You don't change that radical when adding. The next one, we're going to add or work with exponentials. Only like exponential terms, which means they have the same base and the same exponent, may be added. So looking at this first one, we have a few exponentials. Here's a 3 to the 51st, a 7 to the 10th, 3 to the 51st, and a 7 to the 10th. So like ones, there's a 3 to the 51st and a 3 to the 51st. And this is going to be, again, similar to adding like terms. So in fact, I'm going to circle this. I have 2 of these. And how many of these do I have here? Well, I have just 1 of them. So I have 2 3 to the 51st plus a 1 to the 3 to the 51st. So that gives me a total of 3 times 3 to the 51st. And then here, we'll box these in. I have negative 5 of these plus 2 of these, which gives me negative 3. 7 to the 10th. Now this is a good example because we can simplify this more on this one, because we have a 3 to the 1st times a 3 to the 51st. So those are like bases. What can we do with the exponents there? Well, we can add them. So we have 3 to the 52nd. We're not going to multiply this out and see what it is because that's a very large number, 3 to the 52nd, so we're going to leave it like that. Over here, 3 times 7 to the 10th, we cannot simplify that anymore because they're not the same base. We can't do 3 times 7 is 21, because then you would have 21 to the 10th, and that's not, it's a 7 to the 10th times 3, so that's the answer to that first one. We can't simplify that anymore. Our next one, we have a 5 times 4 to the x plus 2 to the 2x plus 3 to the 11th minus 3 to the 10th. This has a couple other things we can work with and learn. So 4 to the x, 4 is not a prime number, so what we can do, it's kind of like simplifying our radicals in our last few examples on the other slide. Well, we can simplify exponents. This is 5, and 4 is really 2 squared, so 2 squared to the x. And then we have plus 2 to the 2x. And these are not the same, but they're the same base, and their exponents are close to each other. So we are going to be able to work with that a little bit. So what I can do here, 3 to the 11th is the same as, I want to get it to look like this, so 3 to the 11th is really the same as 3 to the 1st times 3 to the 10th. And I'm doing that, so I have a 3 to the 10th here minus 3 to the 10th over here. Doing some more simplifying as we work across here. When we have a power raised to a power, we multiply those, so we have 2 to the 2x plus 2 to the 2x. And I'll just rewrite these for right now, and we'll simplify them in the next step. So we have like terms here because we have 5 of these plus 1 of them, because this is like a 1 times this. So we have 6, a total of 6 times 2 to the 2x. And then over here, we have 3 to the 10ths minus 1 3 to the 10th, which is 2 3 to the 10th. I really could have taken this a little bit further here if we want to. For this term right here, so I'm going to say this could be one of our answers, but let's keep going to see if this can be written a little simpler. So we have a 6 to the 2x is really just, we could write 4 to the x, might be an easier way of writing that, and then plus 2 times 3 to the 10th. So up here I changed our 4 to the x to a 2 to the 2x, but we could also go with it this way and have this 6 times 4 to the x power. So either one of those answers will work.